And it's going to do that on me. All right. That's right, I can fix that. Is it recording? It is recording. All right now. And theoretically, I really wish the sound recorder on this thing had a little indicator that it was receiving, but I guess that'll be in some future update. But that's a whole different uproar. Good morning and welcome. We're going to talk about motor burnout. Actually, that's just the title of the slide presentation from our friend Stephen Herman. And we're going to talk about, the first thing we're going to talk about is motor burnout. And you'll see that a lot of things we've talked about in the past are going to be covered in this slideshow. Before you ask, yes, you'll be able to see this again later. And these are the things we're going to talk about: mechanical, things that cause motor burnout, mechanical, poor ventilation, improper wire size. And we've been talking about sizing the wire here in class the last several weeks. Overload heaters, not sized correctly. We've been talking about sizing overload heaters, motor undersized for the load, and over and under voltage and unbalanced voltages. So let's get started. And the first thing that can cause problems with a motor, of course, is heat. And mechanical problems can cause heat more easily than almost anything. It can be caused by a lot of things. And most of these you won't have anything to do with. Poor ventilation, not a lot of things you can do about poor ventilation of a motor. So let's just skip on from that. But a motor not getting enough air to circulate and cool off is going to affect its heating, running temperature. The thing that when we're setting it up, we can definitely size the wire correctly or oversize the wire. We've talked about improper wire size can cause excessive voltage drop at the motor. We're going to talk about voltage drop a little more later. Oops. Sorry about that. Let's go back to our slideshow. And as general, conductors are sized in accordance with the requirements for the NEC. And we've gone over that a lot. We've been sizing the wires and the conduit for our motor block calculations. The NEC requirement states that the conductor for a motor connection has to be based on the values listed in 430-247. Well, 430-247 is one table. That's for DC motors, and 250, as you all know, is for three-phase motors, and 249 is for single-phase AC motors. 430.22 says that the conductor supplying a single motor must be not less than 125% of the full load current. We've done that with every motor we've calculated, and that should be burned in your brain by now. Temperatures of the terminations, we've talked about that several times, but let's talk about that in a little more detail. We've talked about the terminals being rated for the certain temperatures and what to do if they're not marked. The safest thing to do if you're not sure is just go with 60 degrees. But that is not the absolute legal rule. You don't have to do that. 110.14 says that so far as necessary, the lowest temperature rating of any connection, termination, conductor, or device sets the temperature rating of the wire, which is not exactly true. We'll go over that in just a minute. 110.14c is basically stating that regardless of the temperature rating of the conductor, the size must be chosen from the column in which the temperature rating does not exceed the temperature. In other words, the lowest possible column. 110.14c1a says that circuits of 100 amps or less, or wire size 14 through number 1 conductors are to be selected from the 60-degree column in the wire table. And that means if they're not marked, if the terminals are not marked. 110.14c1b permits conductors for circuits rated over 100 amps or for conductors marked larger than number 1 to be selected from the 75-degree column as long as it's a 75 or more degree wire. For instance, you could not use TW to do this. This is where the terminals are unmarked, but this is an exception. We haven't talked about this before, but this is an exception that if the circuit is over 100 amps or the wire is over number 1, then we can select the 75-degree column if and only if the wire is rated for more than 75 degrees or more. Okay, 110.14C1A4 provides an exception for motors with NEMA design code B, C, or D. And what did the design codes have more to do with than anything else? They're more involved with squirrel cage motors and the shape of the rotor bars, and the higher efficiency motors run at a lower current for the horsepower. So because of that, conductors for these motors may be chosen from the 75-degree column, provided the conductors have a temperature rating of 75 degrees or higher. Does not apply to motors that do not list a NEMA design code on their nameplate. So again, presence of a nameplate is a real handy thing. Copper conductors THHN2 installation are to be connected to a 15 horsepower, 240 volt three-phase induction motor. The motor does not indicate a NEMA design code on the nameplate. What size conductor should be used to make this connection? We would look up in, are we on 31016? Is that what we're looking at here? No, we're at 43250. And we're looking at the 15 horsepower at 230 volts. Is that correct? The table indicates a current of 42 amps for this motor. In accordance with 43022A, increase the listing by 125%, which is 52.5 amps. So then we know we need to have 52.5 amp wire or larger, so we then go to 31016 and we would find our 90-degree column. Assuming that all the terminals are 90-degree terminals, table indicates that a number 8 wire with THW2 installation has a current rating of 55 amps. But again, that's in the case where the terminals are 90-degree terminals. Since the motor does not contain a NEMA design code letter, the conductor size must be selected from the 60-degree column of NEC table 31016 instead of the 90-degree column, so number 6 is needed with type THW number 2. So this is not the case of having 90-degree terminals, this is the case of not having terminals, so we'd have to go to the 6-degree column. Improper overload size. One of the leading causes of motor burnout is improper sizing of the overloads. Who is responsible if the motor burns up and you put in the motor starter and the overloads? You are responsible for a year for it running. If it fails within a year, you are buying the parts. Okay, magnetic overload relays can be divided into 2 types, dashpot and electronic. One of the greatest distinctions between magnetic and thermal type overload relays is that magnetic overloads are not sensitive to ambient temperature. Should starters be sensitive to to ambient temperatures? Ambient temperatures affect the motor running temperature, don't they? So probably it would be a good idea. You've seen this dashpot time delay. It's in the lab. You'll see it again. And it creates a time delay to let the motor get started. Electronic overloads employ the use of small current transformers. The conductor supplying current to the motor passes through a CT, a current transformer. Time delay is provided by the electronic timer built into the overload relay. Thermal overload relays sense the motor current by connecting a resistive heater in series with the motor. These are sensitive to ambient temperature, and these are called what? Solder pot. This is a solder pot relay. The trip setting of a thermal overload relay is determined by the heater size used with the overload relay, and that's what we've been looking up in our overload selection guide. Now, the overload heater size, according to 430.32, is used to determine the setting of the overload device. The nameplate current, not the table current. Remember, the only thing you use the nameplate current for is the overload heater. Everything else is code book. Section 430.32 indicates that the motor with a marked service of 1.15 or greater can be, and with a marked temperature rise of 40 degrees centigrade or less, can be set at 125% of full load current. All of the motors are to be set at 115% of the full load current. Those two numbers are taken into consideration in all the overload heater selection booklets from all the manufacturers. So you don't really need to remember that the overloads are 125% or 115%. You just need to know that those are built into the overload selection guide, because when we select it, it says take 90% of the FLA and look it up. Okay, so manufacturers of motor control equipment provide charts that indicate the heater size that should be used based on the full load current on the nameplate. And we have been doing that here in class for several weeks now. Motor undersized for the load. This can only happen when you're first installing the motor and you put in a motor that's just a little bit too small to do the job. All right? When you do that, you are kind of sentencing this motor to a short life. Percentage of motor load that can be determined by measuring the current where the motor is under full load and comparing it to the nameplate value. That means that divide the measured current by the nameplate current, and it says multiply times 100. We're only multiplying times 100 to turn it into percentage, because what we get is a decimal value. Turn that into a percentage, we multiply by 100. So a motor has a nameplate current rating of 26 amps, and the ammeter indicates a current draw of 24.6, so we would divide 24.6 by 26, and we would get 0.984, or 98.4%. One solution to the problem is to install a motor with a larger horsepower rating. Might be a problem if the frame size is too small for a larger motor and it won't fit into the existing equipment. Another solution is to replace the existing motor with a higher service factor, meaning that it can be overloaded. Like a 20 horsepower motor that's rated 1.25 can actually pull many more amps. For instance, a 20 horsepower motor will actually be able to do about 25 horsepower worth of work. Let's see. So there it is, 20 times 1.25 is 25 horsepower. So if you need a little more horsepower and you can't switch frame size, then one of the things you can do is go to a more efficient motor. More efficient motors usually indicate that they're made with larger copper, which costs more money, and that's why probably the earlier version was purchase because it was cheaper. Buying the cheapest thing possible is not always a good idea. Over and under voltage, everybody knows or should know that the voltage supplied to a certain area varies greatly, and it is always not the rated voltage, the nominal voltage. If you think you're getting 230 volts, don't hold your breath. Most likely you do not have 230 volts where you think you have 230 volts. In the lab, we're supposed to have 240 volts or 230 volts. Generally speaking, you'll measure it and you'll find about 208 or 212, 215, something like that. So also, that varies a little bit with the amount of load on the utility, and during the peak load, the voltage will dip just a little bit. Unbalanced voltages, one of the worst operating conditions of a polyphase motor is when it's connected to a system with unbalanced voltages. In other words, the three voltages are not the same when they're supposed to be. When one is slightly out, it's like imagine three horses pulling a load and one horse decides that he doesn't want to work today. It's going to make it much tougher on the whole unit, right? Okay, the most extreme example of unbalanced voltage when a three-phase motor loses one phase, we call that single phasing, and it may continue to work, but it'll pull 173% of its standard current, and if it stops, it will not restart, and if it does try to restart on 2 windings out of 3, it will probably burn up. So a lot of times we've talked about single phasing relays, or I've forgotten the proper term for them at the moment. But we've looked at these relays in our book, and that's what they're for, so that if you lose a phase, that it may shut it down if that's what you set it up for. You can determine the amount of percentage of unbalanced voltage if you happen to have an unbalanced voltage. We're not going to go into that at the moment. Take a look at the examples, though. Subtract the average voltage from the reading that results in the greatest difference. Determine the percentage of difference. And in this case, 4.2 doesn't sound like a great deal, but over 5% is a very bad thing. Well, just keep that in mind, that over 5% is a really bad thing. Determine the percentage of heat rise in motor windings. The amount of heat rise in the windings due to unbalanced voltage is equal to twice the percentage squared. So imagine instead of 4.2 here that we had 5%, so we would have 2 times 5 times 5, so we would have 25 times 2 would be 50% increase in temperature in the windings and the heat. So that would be a really bad thing. All right. That's our first little presentation. And thank you, Stephen Herman. And we're going to talk about a couple more things this morning, but we're going to make separate recordings for those. So we'll stop now.